All right, we are recording. We are live. Can somebody just let me know that the audio, the video, the screen, all that stuff that is coming through clearly? Good. All right, let's go ahead and get started. Okay, so let's go through some logistics and some housekeeping. I did this in concrete design, so I want to do this in steel design as well, just to make sure that both classes are on the same page. So first off, all of the homework is graded as of right now. So I went through and graded homework 7.2 and 7.3, and what I'll say is I found a similar trend on some of the recent homeworks in concrete design, which is that the concrete or the steel design everybody was fine with, or for the most part nobody really had a problem with the actual steel design component of the homework, but it was all the structural analysis and the moment and shear calcs and deflection calcs. That was the stuff that tended to trip people up. And so what I did on homework 7.2 is I just looked at homework 7.2 and I said, okay, if you got the capacity correct, you're good. What we're going to do today is we're actually going to revisit the problem in 7.2, because I think of the class only maybe like 3 of you got the analysis part completely right. And so I kind of want to go through that and make sure that everybody's comfortable on that. We are still going to talk about discretely braced beams, though, so I do want to continue to go through the forward with the lecture in that. All the solutions are posted. The YouTube playlist is up to date as of today. I want to make sure of a couple of things. First off, I mentioned this in concrete design. I'm not sure how, what the announcement or notification system works like for students. As professors, we have a little bit of a different interface with Blackboard, but I believe the way it works is if you go to Blackboard and go to the grade center and look at the homework assignments, you should see your grade on the homework. But if you click that grade, I think there's a chat bubble that pops up. I've been leaving pretty detailed breakdowns for everybody's homework on what they got wrong on the homework. So for instance, if you had a homework assignment and it's worth 10 points and you got 8.5 points, I want you to know why you got 8.5 instead of 10. Like, what did I take off? And so if you look at the homework assignments and go into that chat bubble, there should be some pretty clear step-by-step, okay, well, you got this part wrong, this part wrong, this part wrong. So I really want everybody to check that. Everybody really should take a few minutes and look through that and just make sure that you're clear on what you did wrong, because what we're going to find is that the stuff that we've done in previous homework assignments is going to affect future homework assignments. And what I would hate to happen is I gave you feedback on a given homework, like, okay, you did this wrong, but you didn't see that feedback, and then on future homeworks you just kept doing that same part wrong without knowing any better. Application sharing is reconnecting. Did the screen shut off for everybody? Now is it back? It should be back now. Does everybody see it? All right, I don't know what happened there. I was just sitting there and it just flickered off. I think that happened in concrete design too, but I don't know. Also, one thing I want to mention is Microsoft Teams. If you haven't downloaded Microsoft because I literally just finished grading them just right before class, but I'd say, really the issues were the structural analysis side and the deflection, shears, and moments, not the steel design side. Everybody seemed to do fine on the steel design part. Finally, I am still going to give bonus points for the course evals for concrete and steel, regardless of the new delivery that we've had to endure with the coronavirus outbreak. I am really interested in your feedback in terms of how you think the class has gone. I mean, honestly, especially now that we're at a distance. we've all had to pick up new tricks and learn new techniques, myself included. So I want to know what worked, what didn't. I really value your feedback. And so if you do that and you upload an image showing me that you completed the survey, I don't want to see your individual results. I just want to see that you did it. I'll give you 10 bonus homework points for the semester. Okay, let's get right into it, and let's talk about discretely braced beams. Let me hit control this. Okay, so I got my laser pointer. Okay, let's talk about discretely braced beams. What I want to do right now is I want to take a second and I want to talk about lateral torsional buckling. I want to talk about what do we know so far about lateral torsional buckling. What do we know so far? Okay, and let's take it one step at a time. Okay, so what do we know? The first thing that we know about lateral torsional buckling is that a beam's maximum flexural capacity is the plastic moment, is MP. Or phi MP. I mean, I'm not really talking about resistance factors here, but I'm just talking about the behavior. That the plastic moment is the be-all, end-all, the absolute maximum capacity that a beam can experience. We also know that that's the capacity if the unbraced length is 0. Okay, so if you were to plot the capacity, right? So put put the capacity on the y-axis and put the unbraced length on the x-axis. So at the unbraced length is 0, you should have the maximum capacity. And then what happens past that? Well, we do have a solution for lateral torsional buckling. We derived that last time using those differential equations that I showed you. And again, we don't really need to get into the guts of that derivation. I just want you to know that this is sort of the answer that we came up with. Now, let's just take a look at that equation. That equation is a function of LB. LB is in the equation. LB is the unbraced length. Excuse me. Excuse me, got coffee, went down the wrong pipe. So as the unbraced length gets bigger, like take a look at what that happens to the equation. So unbraced length is in the denominator. The moment is being divided by LB. LB is in the denominator. So as the term LB gets bigger, the moment capacity, the critical moment, gets smaller. So as LB increases, LB decreases. And that makes sense behaviorally if you think about it, because remember, LB is the distance between braces. Well, as those braces get further and further and further apart, the beam gets flimsier between the braces. It gets more slender and gets flimsier, and it wants to buckle more. So as LB goes up, the moment capacity goes down. Okay, so we know that the maximum capacity is MP, and as LB increases, the moment capacity decreases. So if we plot it at LB equals 0, we should get MP, and then it should trail downward, and we're going to see what that looks like here in a second. Now, the other thing that we know is that that equation is limited. It's not good enough, because in order to derive that equation, we have to assume that M is a constant, that the moment is a constant, and that's not correct. I mean, how many moment diagrams do we see that look flat? They don't. I mean, we had that example problem that we did in class where the moment diagram jumped all over the place. It went up, went back down, went back up. And so moments typically are not constant. And so we do have a way of correcting that, and we correct this expression with CB. And so this is the formula for CB. Everybody here should be pretty familiar with that. We did the example in class. You had a homework due at the beginning of class today on this. So this should be pretty familiar. Now, a couple of notes about this formula. Let me go back here because I want to look at this. If you look at this formula is a function of 4 terms, an MA, an MB, an MC, and an Mmax. Now, let's say for the sake of discussion that we have a segment of a beam where the moment is constant, where all the moment terms are the same. So Mmax, MA, MB, and MC all equal one another. If that is the case, if the moment is constant within an unbraced segment, then all these moment terms are the same. And if they're all the same, then on the bottom you have 2.5 plus 3 plus 4 plus 3. So 2.5 plus 3 plus 4 plus 3 is 12.5. 12.5 on the top, 12.5 on the bottom, and CB ends up equaling 1. So the first note about this CB term is that If the moments are constant, CB is 1, okay, if they are all the same. Another note is that if you look at this equation, you can show that for any segment, CB has to be greater than or equal to 1. You can never really have a CB value that's smaller than 1. It's got to be bigger. I mean, because think the Mmax term is always going to be bigger than the MA, MB, and MC terms. And so you can follow the algebra and you can show that CB will always either be 1 or bigger than 1. Okay, and that's going to become important here in a little bit because of the way that we set up our equations for lateral torsional buckling. Okay, so that's what we know so far about beam buckling. Okay, now before we lay out the curve, before we lay out what AISC says about beam buckling, I kind of want to take a step back and talk about column buckling. So I want to look at this. Now, what I have here plotted on the slide is the critical buckling stress for a column. Now let's go back a little bit in a time machine. Let's see if everybody remembers how we did this. So in order to determine the critical buckling stress of a column, first thing you have to do is you have to compute KL over R, the maximum KL over R for a given column segment. And then you take KL over R and you compare it against this term right here. Okay, you compare it against this. And then by comparing it with this term, you can tell whether or not you're in an inelastic buckling region or you're in an elastic buckling region. And so one thing we might call this is a name that we might use for is what's called an anchor point. And so the anchor point might define whether or not we're in the inelastic buckling region or the elastic buckling region. And for columns, that anchor point is 4.71 times the square root of E over Fy. And all that was just setting this equation and this equation equal to one another, and then solving for what value of this makes those two equal, and it's that term right there. Now, let's also remember why we had to use this in the first place. Remember that we use differential equations to derive a critical buckling stress, and we had a nice, pretty equation. We said, that's great. It also doesn't work because there were two reasons why column, like theoretical column behavior and real column behavior weren't the same. There were two differences. And the first was geometric imperfections, the idea that the column isn't perfectly straight and perfectly plumb. And the other is residual stresses, the idea that the beam has locked in internal stresses. Now, I have that on the slide. I have that bolded, the residual stresses, because there's a pretty clear case that we're going to see where the residual stresses are accounted for in the beam buckling curve. The geometric imperfections aren't really accounted for directly. We assume that we kind of have enough lateral bracing to take care of that, but that's really the only point I wanted to that. Well, there's 2 points I wanted to make that to go back to column buckling. The idea that we have an inelastic buckling region and an elastic buckling region that's split up between these, like this anchor point tells you whether or not you're in one zone or another. And then residual stresses had an impact in column buckling. They're going to have an impact in beam buckling as well. So is everybody okay with this before we jump right ahead and just show the beam buckling curve? All right, let's just sort of get right into it. Now, I'm going to go ahead and tell you right now, I'm going to throw a lot of terms, a lot of equations at you, but don't worry, we're not going to use a lot of this stuff today. What I'm going to do today is I'm going to just outline the way that the capacity computes, or the way that the spec computes the capacity of a discretely braced beam, and then on Friday, we're going to exercise this stuff. So today is just sort of, I want everybody to take this stuff in. This is probably, in terms of content, the most content-heavy lecture for the rest of the semester, which is why we're going to let it seep in and exercise it on Friday. Okay, so when we have a wide flange section that's being bent and it's a discretely braced beam, with columns, we split it up into two zones, like inelastic buckling and elastic buckling. For beams, we have three zones. We have the first zone, which is the full plastic moment, which is MP, and that's when we have a lot of braces, or the braces are really, really close together. And then past that, we split it up into two regions, either an inelastic buckling zone, inelastic LTB, or an elastic buckling zone, elastic LTB. So there's three zones. So there's there's full plastic moment, there's the inelastic buckling range, and the elastic buckling range. Now, if you got three zones, you need two anchor points to figure out whether or not you're in zone 1, zone 2, and zone 3. And so those anchor points are what are called LP and LR. So you look at your unbraced length and you ask yourself, well, if my unbraced length is smaller than LP, I'm in zone 1. If it's between LP and LR, I'm in zone 2. If it's bigger than LR, I'm in zone 3. And don't worry, we're going to go through all these terms and equations here in a bit. And so each of these zones has a means to compute the capacity. If you're in zone 1, it's just MP. It's just the plastic moment. If you're in zone 2, we linearly interpolate between MP and this term MR. And MR is just the yield moment that's been reduced, hence the MR, reduced to account for residual stresses. So that's what MR is. And then zone 3, we use that differential equation that you see right here. This is zone 3. It's reformatted a bit. It doesn't look the same, but it's that equation, just reformatted a bit. Now, don't forget, there is also this term CB, and remember, CB is always greater than or equal to 1, okay? So let me just show you the curve. So this is the lateral torsional buckling curve for a wide flame section. So again, this is zone 1. This is when, so here on the x-axis, we have the unbraced length. Here on the y-axis, we have the capacity. So when you're in zone 1, your capacity is just MP, just FYZX. And that's when your unbraced length is smaller than this. When your unbraced length is between LP and LR, we use this linear fit, just this linear interpolation between MP and MR. So that's the zone. The slope of this region, we have a name for that. This slope, we call that the beam factor, or BF. And all it is just a slope. It's just a change in Y over change in X. So change in Y is MP MR, change in X, LR minus LP. That's all this is. That's just the beam factor. And then zone 3, this is the elastic range. This curve is what we derive. This is the solution of that differential equation. Now, that I think is the easy part to understand. What I think is the hard part to understand about this when you first see it is what's going on with this solid curve and this dashed curve. Well, the solid curve is for when CB is 1. The dashed curve is for when CB is greater than 1. And I don't think that this just static picture does what we're talking about justice. I think you kind of have to see it. So what I did is I pulled out an Excel spreadsheet and I did all these calculations to chug it out, and I'll show you the results. This is the pretty part. You don't need to do this. I'm just showing you. So what I have here, and I just picked a random shape. I just picked a 24 by 76. If you go to the manual, you'll see that the plastic moment, the phi MP for a W24 by 76, the phi MPX, is 750. So that's why the curve starts at 750. So that first range is linear, that constant linear. Zone 2 is this straight line fit. And then we've got this parabola. Now what I have here is I have CB is 1. Okay. Now remember, CB is either 1 or greater than 1. So what happens when CB is greater than 1? So let's just start playing around with this. So I'm going to start entering some values. Everybody watch the screen. Let's see what happens. Let's make it 1.05. So if I make it 1.05, it does this. If I make it 1.1, it does this. If I make it 1.15, it does this. So if you look, you should see that the curve is getting bigger. See, CB is greater than 1, so it's making the capacity larger. So the capacity is increasing. So 1.2, 1.25, but that's not the only thing that's going on. The curve is getting bigger, but you'll notice if you look at the very, very top, it's sort of cutting off. So I can make this 1.3, 1.4, 1.6, that no matter what the CB value is, it's always cut off at the very, very top. Remember, the absolute maximum flexural capacity of a beam is MP. That's the maximum, okay? So regardless of whatever it is that you compute, regardless of the capacity, phi MP is the maximum. So when you look at zone 1, the capacity, the equation is zone 1, the capacity is MP. When you look at zone 2 says the capacity is the minimum of a pile of junk or MP. Same thing with zone 3, the minimum of whatever you compute or MP, because MP is always the maximum. So we always cut our capacity off at MP. So when you see the zone 2 and zone 3 equations, that's why there's a minimum of MP. Now let me go back to the slideshow, and let me just start going through the equations. Okay. So again, you determine whether or not you're in zone 1, zone 2, or zone 3 by these anchor points, these LP and LR terms. Now, so with zone 1, your unbraced length is less than LP. Zone 2, you're between LP and LR. And zone 3, you're bigger than LR. Now, here's the expressions for LP and LR. I put here that this LR equation, I'm pretty sure that's the longest equation I have in any of my classes. That LR equation is huge. Don't worry, we're not going to use this equation. We're not going to chug this out at all. We'll never use this, and you'll see why here in a second. And it might seem counterintuitive, but it's actually a whole lot harder to figure out what LP is than LR from a research setting. Like LR may look nasty, but it's really just algebra. You just set your moment, your residual, your reduced yield moment equal to the buckling moment and solve for the length. So it's just a bunch of algebra to get LR. LP requires a lot of experiments, a lot of testing, and a lot of like research to figure out where do we cut that off. So that's just food for thought for later, but it's actually harder to derive LP than it is LR. LR you can do with algebra in about 15, 20 minutes. LP takes a long time. Now, let's look at zone 2 and zone 3. Zone 1, the capacity is just MP, so there's really nothing to say about that. Zone 2, our capacity is between MP and MR. I didn't put subscripts on the MP and MR. I'll do that later. Zone 2 is just linear interpolation. So this equation here in gray, it looks big, but it's just linear interpolation. Well, I've got a simpler way of doing that, and a simpler way of doing that is to use the yellow equation there on the bottom. And the way that we simplify that is, we rewrite it into this minimum expression like we've done before. Remember, whenever we see an equation that's a pile of junk less than or equal to another pile of junk, it's always the minimum. But the other way that we do that is we introduce that BF term. Remember, BF is just the slope of that line. So that's just y equals mx plus b is really all that is. Remember, we got the CB term in there as well. So we always say it's the minimum of whatever we compute in MP. So zone 2 is really, really easy to compute. And most of the beams that we design are going to be in zone 2. You'll see that when we design. Zone 3. Zone 3 is the only one that there really isn't a design aid that we can use to make zone 3 easy. We just kind of have to chug the capacity out. The capacity is the minimum of phi MP or term, the critical buckling moment. And this big equation here is just the same thing that we derived. It's just been reformatted a bit. The reason why they reformatted is because when you look at the equations for like plate girders that are singly symmetric, the equations they look similar. So it's a little easier for the engineer to use because they're somewhat familiar. In order to compute zone 3, you need a few properties. You need the radius of gyration for LTB. So remember, for columns, we had an RX and an RY. We need this R value for LTB. We also need this term H naught. H naught is, if you have an I-beam, H naught is just the distance from the center of the flange to the center of the flange. So it's just that distance. You need J, which is the torsional constant, and you need the elastic section modules. But all that stuff is in table 1.1, so they're just lookups. Now, one note, if you're ever in zone 3, you got to be careful with units. Your LB value has to be converted to inches, because if you look at the equation, you're taking LB, dividing it by RTS, and RTS is in inches. So you got to convert LB to inches to make this work right. Everything else is pretty simple, but make sure you convert that to inches. Now, there's a lot of junk that I've thrown at you in terms of like variables, like base values. Like we have to compute phi-MP, we have to compute phi-MR, this beam factor term, the LP and LR. We don't have to compute any of that, because if you look at table 3.2, the ZX table, they're all there. Okay, look at, here's phi-MP, phi-MR, here's the beam factor term, LP, LR, all that stuff is already computed, so you don't have to go through and do any of that. Remember, I told you that when it's all said and done, we'll know what all these terms are in table 3.2. Here they are. They're all the terms related to discretely braced beams. So what I have here on this slide is probably the most important slide, not only in this lecture, but it's one of the most important slides in the class. This is a flow chart that I developed that will tell you how to compute the capacity of a discretely braced beam. You look at your unbraced length and you say, okay, if my unbraced length is less than LP, I'm in zone 1, here's the capacity. If my unbraced length is between LP and LR, I'm in zone 2, here's the equation. If I'm if I'm larger than LR, I'm in zone 3. I first compute this, then here's the capacity. The only equation that's not listed in the flow chart is CB, and it's right there. That is probably one of the most important slides for the rest of the semester, is that flow chart. We're going to exercise that flow chart on Friday, but before we do, does anybody have any quick questions? All right. Now, we're going to be doing some discretely braced beam stuff Friday and next week before we close everything out. We're going to need to make sure that the structural analysis that we need to do is not a barrier. We had a problem very similar to this on one of the homework assignments, and the actual structural analysis, the moments, the shears, and the deflections seemed to offer a bit of a challenge to everybody. So I want to go through this. Those of you that were in concrete design, we did something very similar in concrete design. I don't want this to be a barrier moving forward, and it's probably more of a sticking issue in steel design, because with discretely braced beams, we need moments, shears, and deflections, whereas in concrete design, all we really needed to worry about, if we really want to get technical, was the deflections from here on out. So this is just a basic structural analysis exercise, no load factors, none of that. I just want to take this beam and I want to determine what's the maximum shear, what's the maximum moment, what's the maximum deflection, and where they occur. I'm probably going to go a little faster in here than I did in steel design, because we've already experienced a problem like this. We just had homework 7.2 where it was just like this. I'm going to go probably a little faster, but I want to make sure that everybody's comfortable with this stuff. So as I'm going through the problem, if you have any questions, please, don't hesitate. All right, so let me share my screen on the notebook. Okay, so here's the problem. And again, I'm recording, so to please, oh goodness, my notifications on my computer are going haywire. Give me a sec. Okay, so here's the problem. Now, the one thing to keep in mind is that there are 3 loads present. There is a distributed load, there is a 15 kip point load, and an 8 kip point load. There's 3 different loads. So with each of these loads, go away. So with each of these loads, we need to handle each of them separately. Now, if you remember in the homework assignment, I referred everybody to case 19, case 21, and case 22. So if you scroll down a bit, I went ahead and screen captured that from the manual. This is case 19, this is case 21, and this is case 22. We're going to handle each of these one at a time, and so this is actually going to be a bit more comprehensive than what you did on the homework. I'm getting a warning that the video quality is reducing a bit. If anybody needs me to repeat a calculation, let me know. Now, we're going to start off with case 19, which is the distributed load. Let me turn my font back to black. Okay. So case 19, the distributed load. Okay, so for this case, I'm going to scroll down a bit, And if you go to the case in the manual, what we're trying to determine is the maximum shear, the maximum moment, and the maximum deflection. So the first thing, let's make sure we're using the right formulas, okay? So the maximum, let's take the maximum moment, okay? This is the maximum moment, WL squared over 2. And then I also want to make sure that everybody's clear as to where that occurs. That occurs at the support, at the fixed end, okay? So that's maximum moment. What about maximum shear? Well, we've got two equations here. One says WL and one says WX, okay? WL or WX is an equation for shear. That's the equation as a function of X. So we're not going to use that one. We're going to use this one. We need a constant value for shear. Now, where does it occur? It doesn't say where it occurs on the slide or on the diagram. But that's what all of this is for, okay? This is the shear diagram. And so this term V corresponds to that term V. And so where does that occur? It occurs right here at the fixed end. So the maximum shear is WL, and that occurs at the fixed end. As for the maximum deflection occurs at the free end, and that's WL to the fourth over 80I. So what do? We go to our distributed load. We recognize that W is 0.8 kips per foot. We recognize that L in this case, the length of the beam is 16 feet plus 9 feet, which is 25 feet. We recognize that E is 29,000 and I is 3,200. So our shear, I'll call it V1. Our moment, we'll call that M1. Let me move that down a bit. M1. And our deflection 1, are computed as follows. V1 is WL. M1 is WL squared over 2. And deflection is WL to the fourth over 8EI. Now remember, I'm not using WL, like let's take the moment. Like we've been using WL squared over 8 a lot for moment, but we use that because it refers to a simply supported beam with a uniformly distributed load. This isn't simply supported, this is a cantilevered beam. So you got to use the right case, the right equation for the right case. We're using WL squared over 2 because it applies to this case. So this is WL, so this is 0.8 kips per foot times 25 feet. And so when you chug that out, that comes out 0.8 times 25 is 20 kips. This is 0.8 kips per foot times 25 feet squared over 2. And that comes out to be 250 foot kips. Make sure you're using the correct units here. Now, for the deflections, 0.8, 25 feet to the fourth, 8,000 KSI, and this is 3,200 inches to the fourth. And as for our conversion factor, don't forget that, we need that here. And 1728 is the conversion factor for deflections, period. It doesn't change if you're using point loads or distributed loads or anything like that. And so when you chug this out, you should get an answer of 0.727 inches. What? My screen stopped sharing. There we go. Can everybody see it now? Okay, good. All right. Now, as for the locations, remember, this occurs at the support. occurs at the support, and this occurs at the free end. And I just want to make sure that everybody is clear on that, okay? Now, I'm going to keep on trucking in the calculations. Again, please don't hesitate if I'm going too fast or if there's anything that you have any questions about, you need me to scroll back up, don't hesitate. All right. So that's the distributed load. And you can see the formulas, and this is where we got them. This is in table 323 in the back of the manual. Now what I want to do is I want to start focusing on the point loads, okay? Now, I'm going to start with the point load that's the easiest, okay? And so that's case 22, which is the concentrated load at the free end. So point load at the free end. So I'm looking at the beam like this. Here's the beam. And I'm looking at the load out here, which the load out here was 8 kips, okay? And the length of the beam is 25 feet. So I'm handling this load case first, then I'll handle the 15 kips later. Now, again, we go to the manual and we see what does the manual say about this load. Okay, so I go to case 22. Oh, I have them in backwards order. Give me a sec. Whoop. I put them in the wrong order. I wanted to do case 22 first. Let me move case 22 up a bit. A little bit of a switcheroo here. Move that up a bit. Okay, that's good. All right, so here's the shear diagram, the moment diagram, the deflections for a cantilevered beam with a point load at the free end. So let's start off. Okay, so maximum moment is at the fixed end, which is the same place as it was before. So when we add all these moments up, add all these shears up, add all these deflections up, they got to be at the same place. And so we want to verify that that's the case, which it is. All right, and so the maximum moment is P times L. What about the shear? All it says about the shear is that the shear is equal to P, but look at your shear diagram. Here's your shear diagram. The shear is constant. So the maximum shear occurs really everywhere because it's a constant shear. You could say it occurs at the fixed end, but it occurs everywhere, and that shear is just P. As for the maximum deflection occurs at the free end, and it's PL cubed over 3EI. So we go through a similar set of calculations. Again, we don't just willy-nilly use formulas. We use the formulas that are appropriate to those cases. So we'll call this V2, M2, deflection 2. So V2, well, hold on. Let's make sure that we got our parameters. P is 8 kips. L is 25 feet. And then don't forget your E is 29,000 KSI. And then I is 3,200. I think I want to make sure I put the right values. Yep, I did. Sorry. Little automatic keyboard keeps wanting to pop up. I'm probably going to have to change some settings to fix that. Okay, so V2 is P. P is 8 kips. And there you're done. M2, P times L, which is 8 kips times 25 feet. 8 times 25, 200 foot kips. Deflection, PL cubed over 3EI. So 8 kips, 25 feet, cubed, 3 I. And last, don't forget your conversion factor. Again, your conversion factor is always 1728, regardless of if you're dealing with point loads, distributed loads, because the deflections, the units come out the same. And so when you chug that out, you should get 0.776 inches. Now, before I move on, I want to say one other thing. I said this in concrete design, and I'll say it in here as well. That 8 kips is a concentrated load at the end of the beam. If you try and say 8 divided by 25 to turn that into a distributed load, bad. No, don't do that. The beam is seeing 8,000 pounds at the end of the beam. If you turn that into a distributed load, you're going to be predicting less moment and less deflection than is actually present on the beam. And that's going to result in an unsafe design. So don't do that. Handle the loads as they are present. And again, just to make sure that we're clear, occurs at the support, occurs at the support, and occurs at the free end. All right. And again, if you need me to hover here for a bit, in fact, I'll go ahead and hang out for a second and see if everybody's good. All right, let's move forward to the last case. So the last case we need to consider is case 21. Now this is the point load at any point. Now what I mean by that is this. What we have is we have a scenario where we've got a cantilevered beam. And just like before, it's a cantilevered beam that's seeing a point load. So it's like the previous case. There's a cantilevered beam that's seeing a point load, but it's not at the free end. It's in the middle of the beam. And we know that based on our problem statement that this is 16 feet and this is 9 feet. Okay, so this you could use, well, this doesn't, well, let's say this, you can't use case 22 for this because the point load is not at the free end, it's in the middle of the beam. You can't use case 22, you have to use case 21. Now let's look at case 21. I have case 21 down here. So here's case 21. Let's investigate our formulas. Okay, so first off, if we look at moment is, again, also at the maximum moment is at the fixed end. The equation's different though. It's not P times L, it's P times B. It's like, okay, what's B? I know what length is, but what's B? Again, go to your diagram. Now, I want to be clear. B is not the distance on the right. It's the distance from your fixed support to the load. That dimension is B. That's what we're talking about. So for this problem, B is 16 feet. L is 25 feet. Because that's L. So L is the length of the beam. B is how far the load out is from the support. Okay. So we've got our maximum moment. We've got our shear, which is P. Again, you know, we have a constant shear, so we can say that occurs at the support. And then our maximum deflection at the free end is computed using this equation over 3EI for this load as well. That doesn't work because it's not the same condition. Okay, the maximum deflection still occurs at the free end, but you have to use a new expression because the load's in a different spot. Okay, so what we've got here, I'm going to drag this up. Again, you should be able to find that in your manual. So we have, again, we've got P is 15 kips. We've got L is 25 foot. We've got B is 16 foot. We've got E is 29,000 KSI. And we've got I is 3,200. So therefore, here, I'll dispense with the therefore. We've got a V3, an M3, and a delta 3. So V3 is just P, which in this case is 15 kips. M3 is P times B, which is 15 kips times 16 feet, which is 240. And then our deflections are, here's the equation, PB squared over 6EI, 3L minus B. And so plug and chugging that out, we have, and I'm going to put all this on top. So we have 15 kips, 16 feet squared. Put this in brackets, so 3 times 25 feet minus 16 feet, and then 29,000 KSI, 3,200 inches to the 4. Again, don't forget, 1728. And so, when you chug that out, you get 0.703 inches. And again, just to make sure we're clear, locations are the same. Occurs at the support. Occurs at the support. And occurs at the free end. All right. I'll give you all a super quick second to catch up, and then I'm going to finish this problem out real quick and show you all the homework. All right. So from here on out, all you have to do is just add everything up. So to summarize, summary. So your V max is just going to be V1 plus V2 plus V3, since they all occur at the same spot. M max, M1 plus M2 plus M3, and then delta max. Just add them up. I'll just do that over here off the side. So when you do that, V max ends up being 43 kips. M max is 690. And delta max is 2.206 inches. All right. I'm going to give everybody a quick sec to see if they have any questions, and then I want to pull up the homework assignment and show you all something real quick before we close today. But does anybody have any questions? If you need me to scroll up and down, I'm happy to. I know I went a little fast, but I figured since we've seen this problem before and we've seen a lot of these expressions before, we should be able to follow it. I just wanted to make sure that I was comprehensive and that I did all the calcs I needed to do. All right. Let me stop the share and pull up the homework. Okay, so here's the homework assignment. I'm giving you a simply supported beam with 2 point loads somewhat inside. Now, I want to make sure that everybody's clear on this. There are 3 loads. There's the distributed load across the entire span, but then there's also 2 40 kip loads. But here's the hint I want to give you. You can actually handle those 2 40 kip loads together. If you review the cases, you will find one case that actually handles both of those 40 kip loads. Like there's a case that has a concentrated load at midspan. There's a case that has a concentrated load at any point. But then there's also one that has 2 loads that are symmetrically placed. So you should be able to find the case that handles both of those together. And what I want to know is for this beam, what is the maximum shear? What is the maximum moment? What is the maximum deflection? And I also want to know where they occur. I want to make sure that, and again, the reason that we're doing this is because I don't want the analysis to trip us up later when we start getting into discretely braced beams. I want the lecture that we talked about when we talked about the AISC spec, I want that to sort of just seep in your head. I want you to sort of chew on that for a bit. And when we start Friday, we're just going to start into that and making sure that everybody's comfortable with the analysis of a discretely braced beam. Any other quick questions before I call it? Do we email the course? No, you can upload it on Blackboard. If you look at the assignments on the bottom, there's a place where you can upload the screen capture, just like you do the homeworks. It's in that same menu. Yeah, I say please don't email them because I'll lose it with all the emails I've got. But don't show me your responses. I don't want to know what you wrote. I just want to know that you did it. Sound good? All right, guys. Well, I'm going to stop the recording. That's all I've got.